Hello everyone, welcome to our new video in R programming. In this video we will see the simple regression model. So first we will start with an example using a survey dataset from the mass library. If you don't have this package in R already installed, then you can run the code here and type install packages mass, and you can install this package. If you already have this package, then you will just simply run this library and include this in our environment. So now we can check. There's a data set here that's called as survey, and there is some student survey data in this example data set, which contains this data frame containing 237 statistics students. There is a conducted survey, and we can check the data set easily. So here is the data set. It contains various columns, as we can see, male, female, and we have the writing hand span in centimeters for each student. So the columns, the variable names are explained here with more details. We are not going to use all the columns, but you can see WR, this is the writing hand, the span, the distance from tip of thumb to tip of little finger in centimeters for the writing hand. Some other data collected, such as the height of each student in centimeters, that is again given here. And for this data set, as usual, we will access the elements, like if we want to access one of the columns, we use the $sign, and then you can, for example, choose the span of the writing hand for each student in centimeters, or you can access to the height. And this is the height for each student in the survey. So we will actually use this dataset to run a simple regression model. But before we do a regression model, it is always good to verify the relationship between our x and y variables. So for this purpose, you can for example, calculate the correlation coefficient between these two variables that you are interested, or we can do a scatter plot. So here we have the plot function. We are using now a formulation for our model. So actually what we write here means we are using a y variable, and we are using the input, which is the writing hand span here, to explain the height of the student. So we are writing a formula for a specific model, which will also be our regression model. So if we run this function here, you can see the scatter plot, and let me make it smaller. This is the writing hand span in centimeters versus the height. So this relationship shows us that basically if we fit a linear regression model, okay, there's a positive slope. We can fit a line to these set of points. In other words, we can use the x-axis variable to explain the height of each student in this survey. Okay, so a positive slope basically different from zero shows that a simple regression model should be suitable. So there seems to be a relationship, association between writing hand span versus the height of the student due to the slope different from the zero. Sometimes you might get a negative slope, right? If the association is indicating a negative relationship between your x and y, then that will again be suitable for a regression model. But with the opposite sign in the relationship. Similarly, we can check the correlation coefficient. Again, the correlation coefficient is positive, just like the slope as we see on the scatter plot is also positive. So one of the things that we need to pay attention when we want to build a regression model is that we need to check for missing observations in our data set. And for this data set, you can actually use isNA function. So this isNA function, we can check the documentation, and basically we will identify at which values our column has missing observations. So for example, when we display our data, this was the height, we have the numeric values, but sometimes we don't have any value that is represented just by this NA. So these NA values cannot be included in our regression. Therefore, we can check for NAs in advance before we set up a model. Okay, and if we run just this part, you see this isNA function returns us true if there is NA. Okay, otherwise it returns false. And we can also do this for the other column. We can do for the writing hand span column and the height, and then we can use an OR operation to take the union of these basically two sets of NAs in different columns, and then you can exclude those. And basically, if we take this OR operation, you can see the result. So we have the union of whenever, if any one of the columns, either the height or the writing hand span, if one of these have NA, then it will return true using this OR operation. And then there is a which function. Again, which function tells us which indices, okay, basically are true. So if we run this, it will return us the index values, index numbers, where there is NA. In other words, NA equals to true for these indices. Which function returns us these numbers. So you can assign, for example, this to a variable incomplete observations, and then you can take the length, and you see that we have in total 29 missing observations in these two columns. So now let's come to the linear model and see how to run the regression. We have a fundamental function here, that's the LM. This is used for fitting linear models, as it is explained here with more details. The basic usage of this function is quite straightforward. You need to give a formulation for your model, in the sense that you have the output first, and then you have the inputs. So that's given as a formula here, and we use this tilde to represent our y variable is explained using several other columns. We use the name of the column, as you see, and we can directly give the data frame. Since we give the data frame, I mean data equals to this data frame, which is survey, you can just represent whichever is your y variable, and whatever is your x variable, you can write the column names. Okay, so this function will recognize this from the column variable names, and since we already input the data here, we don't have to input any other inputs in this function. This is enough for the basic regression model that we want to conduct, we want to run. Okay, so if we assign this to now a variable, let's say this survey fit for as the acronym here, And basically it returns us, as you see, the fitted intercept and the fitted, the coefficient for the right-hand hand span. So the coefficients estimated are immediately given once you assign this to this survey fit variable. Okay, so if you want to, for example, create a plot together with the fitted line, if you want to add a fitted line, you can use the AB line function and just input your fitted model, and you can set the some other optional variables such as the line type or line width, etc. So our plot looks like this one. Now we have the fitted line displayed on the same figure as we have the scatter plot. What else can we do? There are also some other useful functions such as names, like survey fit. So if we apply the names function, basically we can see the different output variables from the regression. And you can use these as you like. For example, let's say you want to access the coefficients. And as you see, I use the $sign as usual and type the name of the variable, and that will return us the content. You can change, for example, the residuals. If you need to use the residuals, that gives you the residuals from the fitted linear model. And furthermore, if you like to access to specific, let's say, X and Y values from your data set, you can again go with the index. For example, at index location 10, I can access and display my X and Y values. So this is the X and Y values. I can store this in this, let's say, point A. And this is the point A with the right hand span and the height for this corresponding student, basically. And there's other functions such as the coefficients that would return you the coefficient of your fitted model. You just need to input your the name for the fitted model, and then again you can display your coefficients here. And then once you want to access to, let's say, one of these coefficients, or each one of these coefficients, then you can again use the index. Here we have two elements in my coefficients, and I can access them by the index 1 and 2. So this is again something that we might guess, similar to our previous examples. And then here we continue. Let's say we choose two observations. Suppose that I want to display on my plot, and I want to add a line, let's say, from these 2 points towards the fitted line. Okay, and for this purpose we have the segment, this segments function. So this is adding line segments to a given plot, and you need to input the coordinates. So these coordinates are given as x0, y0, for example, coordinates of point from which we start drawing, and the destination coordinates are given as x1 and y1. So basically our line will start from x0, y0 coordinates, and it will go towards x1, y1. Okay, so we have x0, y0, but we want to display, we want to do this for 2 points towards the fitted line. So what's the coordinate for what's the y coordinate? Y coordinate is here. We can calculate that by plugging in the x value, right, into the fitted model. As you see, I have now these coefficients beta 0 and beta 1 estimated from the model, and then I can input my x value, whatever value I want to evaluate for the fitted value. You just have the intercept and the slope multiplying this x value. So actually you can do this in a vectorized operation if you want to evaluate this for more than one point. And as you see, I have 2 points, one of them the coordinate for point A and the coordinate for point B. Okay, so these are this is giving us the initial coordinates to start, and then we are going towards this x1 and y1. Okay, so this is our destination coordinates for both of these 2 points. So we are going actually from our fitted line towards the original observation, the coordinate given by x1 and y1. So let's see how does it look like. So first let me run this, and then we can check. And as we will see here, we have these line segments. Okay, so our starting point was on the regression line, and then our end point was defined here. Or you can change the starting point and end point. If it is equivalent, it will not matter. But basically we can see we use the dashed line. The dashed line here, we specify the line type equals to 2. If you want a straight line, you can just change this to 1. And then once we already have the fitted model for our linear regression, basically, then a summary is easily produced using the summary function, and it contains pretty much the most important results about this linear model. We have the regression formula and our data set, and then we have the quantiles, the minimum, maximum, and the quantiles for the residuals. And of course the coefficient estimates, these are the point estimates, and then standard errors are given. And if we divide the estimate by the standard error, then you will get the third value, that's the t value here, and correspondingly we have the p values. So if we want to do the hypothesis test regarding whether these coefficients are significant or not, as long as we have large t values, that means the coefficient is significantly different from 0. That can also be concluded from the p-value. A very small p-value indicates that the coefficient is significantly different from 0. Okay, and furthermore, we can see there are 29 missing observations. The good news is that this linear model will do the fitting by removing these missing observations by itself. So we didn't need to do any special operation, to select the values without NAs. It actually did by itself, and it reports that basically these 29 observations are deleted in this regression. And again, you can calculate the confidence intervals, for example, for your coefficients. That can be done using this confidence interval function, and you simply need to input your fitted model and then decide what's the confidence level you want to use. And similarly, we can represent the names again from the summary. This will show you the names of the variables that are produced from the summary function. You can select one of these and just use it in any part of the code. For example, we can just run this. We have these values that are already obtained. So another useful operation, you can create a histogram, or you can simply plot the residuals from the fitted model. This way you can verify your original assumptions. For example, we can see the histogram, and if the histogram looks kind of close to the normal distribution, that's good news. And also if we don't see any specific patterns in our residuals, that's also good news, because we are assuming that our residuals are identically and independently distributed. In other words, they shouldn't show any specific serial dependence pattern, and they really look like random noise here. So from that respect, we also need to verify our residuals after we have the fitted model. So that's something important. And again, you can actually add new input data, or you can add input data out of the original domain of your observations. If you are adding new data out of the original domain, this is called as extrapolation. If you are utilizing if you are filling the points in the original domain, then this is interpolation. So we have interpolation versus extrapolation. Both can be conducted. So we can write these as numeric values. For example, you can input any value that you want to evaluate your model. Basically, you just need to calculate the predicted value. So this is the predicted value. And then, as we mentioned, you can, let's say, convert your new observations into a data frame, because our original data set is in the format of data frame. So for example, we can convert these 2 points for the writing hand span into a data frame. And then we can say we have some new data. So here we are using another function that's called as the predict function. So this is again a useful function. Once you fitted a linear model, now you have the fitted model, and you can add some new data to this set of observations, and you can use that new data to get new predictions with respect to different confidence interval, for example. So once we run this, that will give us the fit lower and upper bounds for our predictions with respect to the selected confidence interval. And basically, as you see, similar examples can be extended. Actually, you can even have a vector of interpolation values. Suppose you want to use this sequence of values, okay, and we can fill in between many values from our original domain. So we construct basically a finer grid for the x-axis. And then you can use this sequence of values to do your predictions with confidence intervals, actually. Okay, so basically this predict function is quite useful. So we have overall, we have talked about, as you see, the fundamental function here is the linear model function. We can do the fitting, and then we can obtain various results from the fitted model. And also the predict function is quite useful. We can obtain the predicted values as an output from this predict function. You can you can use this function for extrapolation or interpolation. So this basically concludes our example. Thank you for watching this video.